Number 12. A scientist places a rock on a spring balance. Here is a rock and is a spring balance, and this is the length of spring. And hopefully, when you place a rock on it, the spring squeeze, it is compressed, and this length decreases. She then places the same rock on a beam balance. Okay, so here is a beam balance, which actually measures the mass of this rock, and it like the spring is used in Newton meters, which is used to measure the weight of the object. At the North Pole, suppose here is the Earth. Suppose we have a Earth. It's a North Pole. This one is North Pole. North Pole, and here is an equator. Suppose it's an equator, and that's North Pole. Okay. At the North Pole, the gravitational field strength is greater than equator. So suppose gravitational field strength at North Pole is 10, and gravitational field strength is, we are just assuming. Suppose gravitational field strength is 10 here, and gravitational field strength is 9 here. Okay, what's next? She performs the experiment at North Pole and at equator. Okay. How do the reading at the North Pole compare with those at equator? We know that like the gravitational field strength is going to vary, not the mass. So you can say, suppose the mass is, let's assume that mass is 5 kg. Suppose mass is 5 kg. So its weight at North Pole, I'm going to put north here. So its weight would be 510 times 10. Suppose it would be 50. And its weight at equator is 5 times 9. And it is 450. So you can see the weight at equator is small. Weight at equator is small, which is 450, and at North Pole it is large. So let's see which statement is correct about the weight. Beam balance is about mass, so mass remains same. So mass different at North Pole, different at. Okay. Spring is used for weight. So let's see. Different at North Pole. Okay, what is the question? How does the reading at the North Pole compare with those at equator? Oh, yes. It would be different. So different for this one and different for this one. Okay. Same at North Pole, same at North Pole is incorrect. So beam balance is going to measure the mass. So it would be same at North Pole and at equator. So overall, our conclusion is this one, that the spring balance measures different reading at equator and North Pole, but beam balance will show the same reading on both positions. So it means mass remains same, but mass remains same and weight would be changed. Okay, now number 13. Number 13 states, a boy stands on some bathroom scale, which is a weight scale. The reading, okay, maybe mass. The reading on the scale is 50 kgs. What is the mass and what is the weight of the boy? If the mass is 50 kg, then it means its mass is 50 kg. And its weight can be measured with formula W equals M times G. So mass is 50 kg and times 10, it would be 500. So weight is 500. So weight is 500 here. And weight is 500. There is no option for weight. So mass is 50 kg. Okay, mass is 50 kg and weight. So this is the correct option. Okay, now number 14. Two identical beakers contain the same mass of liquid. Two identical beakers contain the same mass of liquid. Okay, there is a different liquid in each beaker, means the masses are same. Masses are same and their volumes are different. Liquid Q has a density rho. What is the density of liquid P? Okay, so there is only a difference of height. Like it looks that their base areas are same. And let's check whether it looks base areas are same, kind of similar. It's an approximate measure. Yes, base areas are same. You can see base is approximately same. Okay. Oh, yes. Okay. So now both have different masses are same. They have same mass. So we can say mass of one is equal to mass of two. So we know that from the density formula, it is mass over volume. So formula for mass would be density into volume is equal to mass. So I can replace it with this. Mass 1 is density of 1 times volume of 1. And mass 2 is density of 2 times volume of 2. Okay, so their volumes are different. Their densities are different. Density of P. So let's consider it as density of P. This is Q. Okay. So density of P is density of Q times volume of Q over volume of P. Density of Q. The symbol for density is rho. Volume is base area into height. The height of Q is 3h and volume of P is base area into height. Both have same base area, so I'm gonna put it like this. So you can see base areas are same. We can cancel out base areas. H is cancelled with H. So we are left with only 3 times rho, which is density of P. So density of P is 3 times rho, which is this option. The mass of paper is paper is sold in packets labeled 80 gram per meter square. It means 80 is the mass of paper and meter square is the area of this sheet. Okay, this means that sheet of paper area 10 centimeters square. Oh, okay. One thing is fine. So we know that the now this is our area. This is area and the mass. This is mass. Area and mass. And the thickness of each sheet is 0.11 millimeters. So this is the thickness. Thickness, or you can say height, but this time it's thickness, so we can say it's thickness. But thickness and height means both. What is the density of the paper? We know that density, the formula for density is mass over volume. So mass is 80 grams and volume is base area into height or thickness. This time it's thickness. Normally we call it base area into height, but this time it is thickness. You can see the area is in centimeter square and thickness is in millimeter square. So we need to convert both of like one of them into the other's unit. So millimeter is a kind of odd type of unit. We can convert it into centimeters. So 1 centimeter is actually equal to 10 millimeters. So now divide both sides by 10. So 10 is cancelled. So 1 millimeter is 1 over 10 centimeters. So it means now if we multiplied both sides by 0.11, so it would become 0.11 millimeters, which is equal to 0.11 centimeters over 10. So now our thickness is this one. We are going to replace 1 millimeter by 0.11 over 10 centimeters, and you can replace it here as well. So instead of thickness, we can replace this value over here. So we are not going to put 0.11, but this time we are going to use this value. And area is already there. So area is this one. So we have values. So let's see. It would be 80 divided by area is 10,000. And it is 0.11 over 10. Okay. This 1 0 is cancelled with this 0. This 1 0 is cancelled with this 0. So we are left with 8 over 100 times 0.11. And we know that if we remove point, it would be 1 in the denominator, and for 2 1s, it would be 0 zeros. So these 2 zeros are cancelled with these 2 zeros. So we are left with 8 divided by 11. If you use calculator, then hopefully it would become 0.7. And then it would be 2, then 7. So 0.727 is an option for density, but it is not 0.7727, but it is 0.73. So this option is acceptable. Number 16. Number 16 says a measuring cylinder contains 20 centimeter cube of water. Okay, here is a 20 centimeter cube of water. A stone is placed in water. Okay, you can see the stone is placed. It is about to place, and in this case it is already placed. And the water level, okay, you can see the previous volume of the water was 20 centimeter cube, and this is the new volume of the previous volume of water, and this is the new volume of water. So now we have two different volumes. If we just subtract them, suppose new volume minus old volume is the volume of this stone. So 38 was the previous volume of the liquid, and 20 is the new volume of the liquid. So it would become 18, which is the volume of this stone. What is the volume of stone? Oh, simple. It's a very simple question. So this is the volume. Oh, that's simple. So simple. Okay, now number 17. A spacecraft travels from the Earth to the moon. At a certain point in a journey, it has zero weight. Oh, its weight becomes zero. So let's see what is the possibility. We know that in case of weight, we have only two possibilities: mass times gravitational field strength. So if as long as the spacecraft is present, it will have some mass. So mass is not going to be zero. It means gravitational field strength is zero. And gravitational field strength becomes zero when the spacecraft is beyond the Earth's gravitational field. Suppose this is our Earth, and around the Earth we have a certain region within which there is a gravitational field influence of gravitational Earth, that is gravitational field strength. Suppose we have this is our spacecraft. Suppose as long as the spacecraft is within this circle, which is the gravitational field around the Earth, it will have some weight. Once it crosses this gravitational field strength, it will be out of Earth's gravitational field, and its weight would become zero. So the reason for zero weight is actually the crossing of this gravitational field. Once it would cross the gravitational field, its weight would become zero. So let's see the possible options. the gravitational field of the earth and the moon cancel each other. No, there is no such type of thing. They don't cancel out each other because the gravitational field of the earth is much more larger than the gravitational field of moon. The spacecraft stops moving, like it's going in outward direction. There is no air resistance. There is no link of weight with the air resistance. In the formula, there are only two things: mass and gravitational field strength. It means either of them would become zero. So we can see that there is only one possibility, which is spacecraft leaves the Earth's gravitational field. So that's the possible option. Okay. Number 18, the weight of a cylinder on the moon is less than its weight on the earth. Okay. On moon, like the formula for weight is W equals mg. And suppose cylinder has mass, whatever, m. But gravitational field strength is 1.62. So its weight is 1.62 times m. And let's see the weight on Earth. Weight on Earth. So weight on Earth is the same formula. So mass is m. Gravitational field strength is 10. So it is 10m. Okay. Now, what the thing which makes the difference is gravitational field strength is 10 here, and gravitational field strength is 1.6 here. So gravitational field strength of the moon is smaller than the gravitational field strength of the Earth. So let's see the possible options. How do gravitational field strength and the mass of the cylinder on the moon will compare to the values on the Earth? Okay, you can see mass is same whether it is on Earth or whether it is on moon. So mass is not going to change. Mass on moon is the same. Okay. And what about gravitational field strength? Gravitational field strength is 10 on Earth, and gravitational field strength is 1.62 on moon. So gravitational field strength is less on moon. So gravitational field strength on moon is less than on Earth. So this is our possible option. Okay.